This video is about series and error. So we're going to explore the graph of this series, which is not geometric, and we're going to observe a pattern and add terms one at a time until we can answer things pretty confidently. So what we're going to do is we're going to go to Desmos here. We're going to start with y equals x. Then we're going to put on the next term, x minus x cubed over 3 factorial. That's going to look something like a cubic polynomial. And then we have a fifth degree polynomial when we add the next term. Then we have a seventh degree polynomial that kind of dip-de-doos even more. And so the series can be represented by this monstrosity here, negative 1 to the n minus 1 times x to the 2n minus 1 over 2n minus 1 factorial for the sum of n equals 1 to infinity. So since Desmos can't do infinity, I'm just going to continually add terms. So we'll start with a equals 1. Notice that it's just going to mimic the first 4. So 2, 3, 4, and then it starts doing more terms as I continue to add terms, so 12, 13, 14, 15, and so on. And so what I'm going to do now is get rid of the first 4 versions of this and kind of just look at what this graph looks like. And this graph looks a whole lot like sine of x. And so if I look at what this graph looks like, it appears to mimic sine of x really well. And we can even see that if I change the x-axis to things that we're used to for sine. You can see that the graph of sine of x looks exactly like the graph of this series. So as we kind of looked at it, we saw, oh my goodness, this kind of looks like y equals sine of x. And the interval of convergence appears to be everywhere. If I go back to this thing, if I keep adding things more and more and more, it looks like it keeps mimicking this for a very long time, and then it stops. Well, if I add more terms, it's going to mimic it even longer. It just takes a while for Desmos to kind of figure it out. So as we see, this looks a whole lot like the graph of sine of x for a very long time. And the more terms I add, the more terms that this polynomial, or the more likely it is that this polynomial will keep going forever and ever and ever along sine of x. We just can't see it because Desmos takes a while to figure out. So the interval of convergence would be negative infinity to infinity. We're going to do a few homework problems now. Problem 3 from the homework. This series, A, determine the ratio for the polynomial. So the ratio in this problem appears to be we're multiplying by 2x every time. And also note that a sub 1 is x. So when I write the rational function as a sub 1 over 1 minus r, that's x over 1 minus 2x. Use the ratio 2x to determine the interval of convergence. The interval of convergence, if I write it as 2x is less than 1, but it's greater than negative 1, I find out that my interval is from negative 1/2 to positive 1/2. So now I'm going to start plugging in x equals 0.5. So I want to use the first 3 terms of the polynomial. So that would be just these 3. So if I plug in 0.5, I get 0.5 plus 2 times 0.5 squared plus 4 times 0.5 cubed, and that ends up being 1.5. It's always 1/2, basically 1/2 plus 1/2 plus 1/2. So that is my sum. The function r of x at 0.5 is 1.5 over 1 minus 1. Oh, that's something 0.5 divided by 0. This is undefined. So I have an undefined error. And, well, that makes sense. If you think about the actual graph of this, there is an asymptote at 1/2. So therefore, this function will not ever approximate this at 1/2. And I should have known that because my interval of convergence does not include 1/2. There's a parenthesis here, so that's not going to work. So how many terms are needed to guarantee that the error is less than 0.1? It'll never work. Now, what if I change this to negative 0.5? Now, all of this stuff is going to end up being the same, like parts A, B, and C. That stuff doesn't change. Nothing about that changed in this problem. So then the question is, what happens when I start plugging in negative 0.5? At least the denominator works. So I'm going to do my sum, negative 0.5 plus 2 times negative 1/2 squared. That becomes positive 0.5 minus 4 times an eighth. That's negative 0.5. So negative 1/2 is my sum. Notice what happens with my sum. My sum just constantly alternates. This is negative 1/2. This is positive 1/2, negative 1/2, positive 1/2, and so on. If I plug in negative 1/2, it's just going to be an alternating series of negative 1/2 and positive 1/2. So if I'm at an odd term and I stop, it's negative 1/2. If I'm at an even term and I stop, it's 0, because negative 1/2 plus positive 1/2 cancels out. Then this would cancel out. So it just kind of depends on where I stop, but it never converges to something. And that's why this was also not part of the interval of convergence. Notice that negative 1/2 has a parenthesis. Now, if I picked anything in between negative 1/2 and positive 1/2, it would converge. But because I chose both endpoints in the previous two problems, it's not going to work. So the sum is negative 1/2, but the function value at negative 1/2 for my rational function is negative 1/2 over 2, which is negative 1/4. So my error is 1/4 if I take the absolute value of the difference. And then if I look at what happens with this problem, if I increase my sum, notice that I just continually increase the amount of terms. It's breaking off before I get to negative 1/2, and there was an asymptote at positive 1/2, so it certainly wasn't going to work. But notice that my error is always 0.25. So this error is always 0.25 if I subtract the rational function from the series. It's always 0.25. And that's because, let's say my rational function is negative 1/4. Well, my sum was either negative 1/2 if I stopped after an odd number of terms, or if I stopped after 4 terms or 6 terms or 8 terms or something, it was 0. We already talked about that. Well, 0 minus a fourth and negative 1/2 minus negative a fourth, the absolute value of that is always 1/4. So the error never changes. The error never gets closer to 0. And therefore, since the error is always, there's always a big error, basically, it never gets closer to 0. It does not converge. And it wasn't in our interval of convergence. So kind of makes sense. Now let's look at this last problem. The ratio First of all, my A1 is 2, and my ratio in number 5, which is the one we're doing, is negative x over 2. So my rational function here is 2 over 1 minus negative x over 2, or plus x over 2. If I simplify this by multiplying everything by 2, here's my rational function. So 4 over 2 plus x. Then if I want to take the absolute value of r and set it less than 1, my interval of convergence is negative 2 to 2. If I plug in 1/2 into the first 3 terms of the sum, 2 minus a half plus 0.5 squared over 2, that ends up being 2 minus a half plus an eighth. So my sum ends up being 1.625. The actual value of the function at 0.5 is 4 over 2.5, which is 8/5 or 1.6. So my error is the absolute value of when I subtract them. That's 0.025. And if I add one more term, the sum after 4 terms, it was 1.59375, and my R value was still the same. So if I subtract those things, the error is 0.00625, which is definitely less than 0.01. So all I need is 4 terms for that. Just 2, my error is 0.4. Then 2 minus x, the error becomes 0.1. Then 2 minus x plus x squared over 2, the error at 0.5 becomes 0.025. And the error just keeps getting smaller and smaller and smaller as my polynomial keeps getting bigger and bigger and bigger. So at 0.5 right here, if I zoomed in really, really, really far, the error here is not very big as I make this polynomial closer and closer. Now, there was a big error, then it gets smaller, 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 and smaller, smaller. So the error ends up getting a lot smaller as time goes on.